In 2023, forecasters told California to brace for a dry winter. That year was shaping up as a La Niña year, and La Niña, according to decades of established climate science, is supposed to mean drought conditions across the southwestern United States. Instead, California had its 10th wettest year on record. The reason turned out to have nothing to do with El Niño or La Niña at all. It came down to a phenomenon scientists were only beginning to fully understand. Atmospheric rivers, long plumes of concentrated moisture in the sky, arriving not as isolated storms, but stacked back to back in rapid succession, overwhelming a seasonal forecast that should have predicted the opposite outcome. Now, in 2026, as a genuine super El Niño builds toward what could become one of the strongest events ever recorded, scientists studying that exact same mechanism have found something new, and this time, it is not working in California's favor. New research shows that during strong El Niño conditions, specifically, these same atmospheric rivers do not simply become more frequent. They cluster together into extended sequences capable of producing some of the most extreme sustained precipitation accumulations California can experience. Today, we're going to explain exactly what scientists just found, why this specific super El Niño is developing under conditions the planet has genuinely never experienced before, and why all of this adds up to a uniquely dangerous setup for California this winter. If tracking the real science behind extreme weather, not just the scary headlines, is something you want to keep doing, subscribing means you catch the next update the moment new research comes in. Let's start with what El Niño actually is, because understanding the basic mechanism makes everything that follows make sense. El Niño is a naturally occurring climate pattern involving a periodic warming of surface waters across the central and eastern tropical Pacific Ocean, part of a broader multi-year cycle called the El Niño Southern Oscillation. That warming reshapes atmospheric circulation patterns across the entire globe, typically shifting storm tracks in ways that bring wetter conditions to the southern United States, including California, while pushing warmer, drier conditions across the northern tier of states. On June 11, 2026, NOAA officially confirmed that the Pacific had entered this warm El Niño phase, and forecasters have been increasingly direct about just how strong this particular event could become. The mechanism behind that global reshaping starts with something surprisingly straightforward: warm water. When surface temperatures across the central and eastern tropical Pacific climb well above average, that warmth transfers directly into the atmosphere. Above it, altering where thunderstorm activity concentrates and, in turn, shifting the position of the jet stream, the high-altitude river of fast-moving air that steers storm systems across the globe. A jet stream nudged further south than its typical position tends to funnel more storm systems directly toward California and the southern United States, while a jet stream pushed further north can leave the same regions unusually dry. El Niño's warm Pacific water reliably pulls that T-jet stream into the configuration favoring wetter conditions across California, which is the basic physical reason the state has historically watched incoming El Niño forecasts so closely. Current projections put the odds at somewhere between 60 and 80% that this El Niño strengthens into what scientists call a very strong or super El Niño by the peak of winter, a designation that has only been recorded a handful of times since reliable record-keeping began in 1950. Here is what makes this specific event genuinely unusual, according to the scientists tracking it most closely. Daniel Swain, a climate scientist with the University of California Agriculture and Natural Resources, put it about as directly as a researcher can. The world has never experienced a strong or very strong El Niño arriving on top of a global baseline that was already this warm. Every previous major El Niño on record developed against a cooler overall planetary backdrop than the one this event is forming within right now. That distinction matters enormously, because it means forecasters cannot simply look at how past El Niño events played out and assume this one will behave the same way. Swain's own assessment was blunt. It would not be surprising to see genuinely unprecedented global impacts by later this year into 2027 across flooding, drought, and wildfire extremes alike, precisely because this event is unfolding in conditions with no direct historical precedent to compare against. Now let's get to the specific new research that ties directly into what California is actually facing this winter, because this is where the something scientists didn't expect part of the story becomes concrete rather than abstract. For years, water. Managers and forecasters have relied heavily on the general rule that El Niño years tend to bring wetter conditions to California, while La Niña years tend to bring drier ones. That relationship held up reasonably well as a broad seasonal guideline, but it never fully explained why some El Niño years produced only modestly above average rainfall, while others produced genuinely catastrophic flooding. New peer-reviewed research, again involving Swain's research group, has identified the missing piece. Atmospheric rivers, the long, narrow bands of concentrated water vapor that already account for the majority of California's annual precipitation and virtually all of its worst, flooding events do not simply become somewhat more frequent during strong El Niño conditions. According to the study's findings, the temporal clustering of atmospheric rivers into what researchers call longitudinally oriented families, essentially back-to-back sequences of storms following closely related tracks across the Pacific, is more than twice as likely to occur during El Niño conditions compared to other years. The same research found a substantially elevated likelihood of month-long storm sequences, capable of producing very large cumulative precipitation totals, specifically under moderate to strong El Niño conditions. To understand what an atmospheric river family actually looks like in practice, picture a conveyor belt stretching across the Pacific Ocean, feeding one storm system after another toward the same general stretch of coastline along a similar track. Rather than each storm forming independently and arriving at a somewhat random interval, a family of atmospheric rivers follows a shared longitudinal alignment, meaning the same broad atmospheric conditions that produce the first storm remain in place long enough to funnel a second, a third, sometimes a fourth system along nearly the same path within a matter of weeks. Researchers describe this clustering as longitudinally oriented specifically because the storms tend to stay aligned along a similar north-south corridor as they cross the Pacific, repeatedly targeting the same general stretch of the California coastline rather than spreading their impact more evenly across the broader west coast. It is worth pausing on why that clustering effect matters so much more than a simple increase in average rainfall would. A single atmospheric river, even an intense one, typically allows some recovery time afterward. Soil has a chance to absorb the moisture. Rivers have time to recede, and reservoir operators have room to manage releases before the next system arrives. A family of atmospheric rivers arriving in rapid succession removes almost all of that recovery time. Each subsequent storm lands on ground that is already saturated, rivers that are already elevated, and reservoirs that already have less spare capacity than they did before the sequence began. That is precisely the mechanism behind some of California's most destructive flooding events in recent memory. Not one massive storm, but a relentless procession of storms arriving close enough together that the state's flood infrastructure never gets a genuine chance to reset between them. California's reservoir system is specifically designed around the assumption that storms will arrive with enough spacing to allow controlled releases and genuine capacity management between events. Reservoir operators typically hold back a portion of storage capacity heading into the wet season precisely to absorb a major storm's inflow, without requiring an immediate, large-scale release downstream. That buffer works well against isolated storms, even intense ones, but a clustered family of atmospheric rivers can force operators into a much more difficult position, releasing water ahead of an incoming storm simply to maintain flood control capacity, only for the next storm in. The sequence to arrive before that released capacity can be fully replenished under normal, careful management. That is a large part of why the specific pattern this new research describes concerns water managers so directly. It does not just add more total rainfall to a season, it changes the operational math behind how safely that rainfall can actually be managed once it arrives. This is also, notably, not the first time atmospheric rivers have overridden what a standard El Niño or La Niña forecast would predict, which is exactly why the framing of this pattern doing something unexpected, once again, is accurate rather than simply dramatic. Researchers at Scripps Institution of Oceanography at UC San Diego published a separate study examining exactly what happened during that surprising 2023 La Niña winter, when California experienced 9 separate atmospheric rivers that combined to produce its 10th wettest year on record, despite La Niña conditions that should have pointed toward drought. Their conclusion was direct. Atmospheric rivers can overwhelm the influence of El Niño and La Niña on annual precipitation totals across the American West entirely. A finding with real implications for water managers who have historically leaned heavily on ENSO forecasts to plan reservoir operations months in advance. That 2023 case is worth understanding in a bit more detail, because it is genuinely the clearest historical example available of exactly how badly a standard seasonal outlook can miss the mark once atmospheric rivers get involved. Water managers, heading into that winter, had every reason to plan for a drier than average year, since La Niña conditions were firmly in place in decades of historical data supported that expectation. Instead, 9 separate atmospheric river events arrived over the following months, several of them clustering closely enough together to overwhelm the drought-focused planning that had gone into that season, ultimately producing the state's 10th wettest year on record despite a seasonal forecast pointing firmly in the opposite direction. That earlier research already demonstrated atmospheric rivers could scramble the expected outcome of a La Niña year. This year's new findings show the same underlying mechanism working in the opposite direction, not scrambling an expected dry pattern into an unexpected wet one, but taking an already expected wet El Niño pattern and organizing it into the specific, clustered structure most likely to produce genuinely extreme, sustained flooding. Put all of this together, and the picture facing California this winter becomes considerably more specific than a generic wet season warning. This is a state entering a strong to super El Niño winter, with research showing that exact climate phase roughly doubles the odds of the specific storm clustering pattern responsible for the most severe flooding outcomes, arriving on top of a global baseline warmer than any previous strong El Niño has ever formed within. Emergency planning resources circulating ahead of this winter have described California facing a genuinely compound risk picture rather than a single hazard. Wildfire conditions persisting into the start of the wet season, atmospheric river flooding, mudslides, public safety power shutoffs, and evacuation traffic all layered on top of each other, with the real danger being less about any single disaster type and more about how rapidly the state could be forced to swing between dry, fire-prone conditions and sudden extreme precipitation. That whiplash pattern deserves specific attention given everything California has already been through this year on the fire side of the equation. Areas scarred by wildfire lose the root systems and vegetation that would normally help stabilize hillsides and absorb rainfall, leaving burned slopes dramatically more vulnerable to mudslides and debris. Flows even from rainfall totals that would pose little risk to unburned terrain. A winter defined by clustered atmospheric river families arriving in rapid succession is precisely the scenario that turns a recently burned hillside into a genuine mudslide hazard, since saturated, unstable ground gets hit again and again before it has any chance to stabilize between storms. The physical mechanism behind that heightened risk is well documented by geologists who study post-fire landscapes. Healthy vegetation and root systems act like a natural anchor, holding soil in place on a slope, and slowing the rate at which rainwater actually penetrates the ground. Once fire removes that vegetation, and particularly once intense heat bakes the top layer of soil into a water-repellent crust, rainfall that would normally soak in gradually instead runs off rapidly across the surface, picking up loose ash, soil, and debris as it goes. A single, intense storm can already trigger a dangerous debris flow under those conditions. A clustered sequence of storms arriving one after another removes any window for that scorched soil to begin recovering, or for early erosion to settle, compounding the hazard with each successive system rather than allowing it to gradually ease. Given how severe this year's fire season has already been across large stretches of the American West, that intersection between burn-scarred terrain and an unusually clustered wet season is exactly the kind of compounding risk emergency planners are watching most closely heading into winter. There is a secondary, less immediately dangerous, but genuinely fascinating consequence of this super El Niño worth understanding as well, because it illustrates just how far-reaching these ocean temperature shifts actually are. El Niño disrupts the cold, nutrient-rich upwelling that normally sustains the marine food chain along the California coast. Chris Lowe, a marine biology professor and director of the Shark Lab at Long Beach State University, has described the resulting shift as creating an entirely different ocean environment, one where species like squid, anchovies, and sardines get pushed north out of their typical range, and where previous strong El Niño events have coincided with unusual sightings of species like hammerhead, tiger, and bull sharks appearing off the California coast well outside their normal territory. That kind of ecological disruption will not make headlines the way a flood or mudslide does, but it reflects the same underlying reality driving every other consequence discussed in this video. A strong El Niño does not simply add a bit more rain to an otherwise normal year. It reshapes ocean temperature, atmospheric circulation, and storm behavior across an enormous stretch of the planet simultaneously. Upwelling itself is worth understanding briefly, since it is the mechanism tying the ocean disruption directly back to the same warm water process, driving everything else in the story. Under normal conditions, wind patterns along the California coast push surface water offshore, allowing colder, nutrient-dense water from the deep ocean to rise up and replace it, fueling the phytoplankton growth that forms the base of the entire coastal food chain. El Niño's warm surface water effectively caps that process, suppressing the upwelling that would normally occur and leaving coastal waters both warmer and less nutrient-rich than usual. Fish and other marine species that depend on that nutrient-rich water respond by shifting their range in search of better conditions, which is exactly the redistribution Professor Lowe and other marine biologists have documented during previous strong El Niño events. It is important to be precise about what this research does and does not actually guarantee, because even the scientists behind these findings are careful not to overstate their certainty. A very strong El Niño does not lock in any single specific outcome for California's winter, and researchers studying this pattern have been explicit that no two El Niño events play out identically, since local atmospheric conditions can still push a given winter's actual weather away from what the broader climate pattern alone would predict. What this research does provide is a meaningfully sharper probability picture than existed before. Evidence that a strong El Niño event specifically elevates the odds of the exact atmospheric river clustering pattern most associated with California's worst flooding winters, layered onto a global climate baseline warmer than any previous strong El Niño has ever had to work within. That combination is exactly why emergency planners and water managers are treating this winter's outlook with more specific urgency than a routine seasonal forecast would normally warrant. If you live anywhere in California, here is what is actually worth doing with this information well before the first major storm sequence arrives. Check whether your home sits in or near a recent wildfire burn scar, since those areas face dramatically elevated mudslide and debris flow risk during exactly the kind of clustered back-to-back storm pattern this research suggests is more likely this winter. Clear rain gutters and drainage channels around your property now, before the wet season begins, since a single blocked drainage point can turn a manageable storm into localized flooding once several systems arrive in close succession. Know your community's flood and evacuation zones in advance, and keep a go bag with essential documents, medications, and supplies ready, since California's flood emergencies can develop with considerably less warning than a wildfire evacuation typically allows. And follow official sources like the National Weather Service and the Center for Western Weather and Water Extremes for real-time atmospheric river forecasts throughout the winter, since these systems are now tracked and rated with increasing precision well before they make landfall. The Center for Western Weather and Water Extremes specifically rates incoming atmospheric rivers on a scale from 1 to 5, similar in spirit to how hurricanes are categorized, factoring in both the intensity and duration of an approaching system to estimate its likely impact before it ever reaches the coast. Following that rating system throughout the winter gives residents a genuinely useful, evidence-based way to gauge whether an approaching storm is a routine rain event or part of the kind of extended high-impact sequence this year's research suggests has become significantly more likely, rather than relying solely on general seasonal outlook language issued months in advance. What scientists have found heading into this winter is not simply that a big El Niño is coming. Forecasters have been saying that for months. It is that the specific mechanism responsible for California's worst flooding winters, clustered families of atmospheric rivers arriving with almost no recovery time between them, is measurably more likely during exactly the kind of strong El Niño event now taking shape, arriving on top of, global conditions warmer than any previous strong El Niño has ever formed within. That is a genuinely new, more precise piece of science, not a repeat of last year's warning with slightly scarier language attached to it, and it is exactly the kind of distinction worth paying attention to before dismissing another El Niño headline as more of the same. We will keep tracking this super El Niño and the atmospheric river research behind it as new forecasts and new storm sequences develop throughout the winter. If you want those updates the moment they land, subscribing is the way to make sure you do not miss them. And if you live in California and remember how the winter of 2023 actually played out, tell us in the comments what that season was like for you, because understanding how atmospheric rivers already broke. One seasonal forecast is exactly why this new research deserves to be taken seriously, rather than dismissed as just another exaggerated headline, especially heading into a winter with even more uncertainty layered on top of an already unprecedented climate baseline. Stay safe, and we will see you in the next one.